Hello, everyone. We are looking at model selection. So I may have far too many variables in my model, 50 variables, and maybe many of them are noise variables, I don't know. And if so, I want to get rid of them. We have looked at all possible subsets, which is the optimal approach, but even with 50 variables, that will not be feasible typically. So instead, we're looking for an alternative way to search through potential models that considers far fewer of them. And we look at three sequential approaches: forward selection, backward selection, which is also called backward elimination, and a hybrid method between the two. Okay. We'll start with forward selection in this segment. And I have divided this into sort of the modern approach using AIC and the more traditional approach using p-values or equivalent things. So in the modern approach using AIC, I start with the null model or the empty model, the model that only has the intercept here. You see the beta 0, but nothing else. And now I select the best variable among the p variables that I have available and add them to the model. By best, I mean the variable that leads to the model that reduces the AIC most. If I don't get a reduction in AIC, I stop. But otherwise, I continue on and on, each time selecting the best variable. So I generate a sequence of variables until I can no longer improve the AIC. Okay, so I call this the modern approach because it uses the AIC. We will talk about the differences to the traditional approach in a bit. Here are the Bush data that we have seen before in the case study. And here in R, we have this function step AIC. This does the work for us. And you see here the model. We start with an empty model. This just has the intercept. The intercept is the 1 here, right? And then we have a final model. This is what the procedure selects in the end. And then we have steps in between what it does when. And so the initial model had an AIC of minus 473. Then you added income, the AIC went down. You added Bush 2000 PC, AIC went down, AIC went down. Added Hispanic, AIC went down. And then anything you did after that, adding any other variable, didn't lead to a decrease of AIC, and that's why we stopped at that point. Okay, so we'll leave that there, and now we will talk about the traditional approach to forward selection based on p-values. Again, we start with the null model, and again, we enter the best variable at each step. The difference is now we have a different criterion, p-value, and we have to set a threshold how significant a variable has to be in order to be entered. So for example, you could say my threshold for including variables is the variable has to be significant using a significance level of 5%. And if so, then I add the variable. So I wrote, the p-value here. Here I wrote the R-squared, that's an equivalent criterion. So I enter variables one at a time. And each time I enter a variable, I have to recalculate all p-values because they change conditional on previous p-values, on other variables. And when I have no longer a significant variable, I stop. So I just alluded to this. There are several equivalent criteria. If I choose the model that leads to with the most significant variables, or the variable with the lowest p-value, that is the same thing as saying I'm choosing the model that increases R-squared most, or the variable that reduces the sum of squares errors most, or the variable with the largest absolute t-value, right? Because large t-value is small p-values. So all of these things are completely equivalent. So why is it then that I call the algorithm that is essentially the same, that uses p-values or R-squared, traditional, but I use the one that, but the similar or same algorithm that uses AIC, I call that modern. It's because repeated selection on p-values has theoretical problems. It's the so-called multiple comparison problem. The p-values from the second step onwards are not correct because their calculation ignores the repeated sequential selection in previous steps, and it should account for that. Because in the second step, the model isn't fixed. You didn't start with that and then you compute p-values. Really, you did something else beforehand, and that uncertainty is not accounted for when you compute the p-values in the second step. So there are ways of adjusting this, but it's a little bit complicated. We're not doing that here. Actually, it's very complicated. And so the complaint is only about the magnitude of the p-values. It's not about the relative ordering. So when I say a variable is the best and then the next variable is the best, that remains true. It's just that the interpretation of the p-value is incorrect because it should be a different value and we don't know what it is. So we exploit this phenomenon. We can exploit it because the ordering is correct, the p-value is incorrect, by simply doing a variation now on the modern approach with AIC. We can use the traditional algorithm to generate an order of models, a sequence, if you will, and evaluate the AIC of each model. And then among the, I don't know, 8 or 10 models that were chosen through that search space, using the traditional algorithm, we pick the one that has the lowest AIC. And this variation on the modern approach evaluates the sequence of the model without using the p-values. And because it doesn't use the p-values, it avoids the multiple comparison problem. All right, so here we have a clicker question. I have the Bush data again, and I have the regression here, right? Regression on all or on many variables. And the question now is, which variable is first entered in forward regression? I will leave you to answer this, and I'm moving on. Here is the same model, but here I'm actually going through with the forward selection. Okay, so in Stata, forward selection is called, well, as well as backward and stepwise, it's called just stepwise. It comes as a prefix before the regression command. And so you see here, this is the prefix, everything before this is the prefix. And we specify the probability to enter at 10%. That is just a choice. A variable has to be significant at 10% before I enter it. Then it turns out that the first variable, the most significant one, is income. We have a significance level of 0.00004, definitely better than 10%. Then in the next step, we add another variable, and that's the next best one, conditional on income being there, and that's push 2000 PC. And we look at the p-value, and it's 0.00001. And we say, oh, wait, that p-value is smaller than the original p-value. The algorithm made a mistake. No, they did not. Once you add a variable in the model, p-values change. And usually, when you add a variable in the model, you expect the next one to go up. That would be the normal case. Here we have an unusual case that the probability of the second variable, conditional on the first one already being there, is lower than the best one if I just look at one variable at a time. And if you look at it, the full model, which is down here, here the probability is 12%. And well, that's a fall from grace. It had 0.0004% when it was alone. And then given that it's correlated with the other variables, once you put some all other ones in, it goes down to 12%. And it wouldn't even have qualified for our 10% limit because it's above 12% now, right? Things happen. All right, so Stata didn't make a mistake here. It's just that the variables are correlated with one another and the p-values change. All right, so moving on. want to make one more comment on this. I chose a probability to enter value of 10%. So that's that significance level, right? And why did I choose 10% than not being rather than 5%? And the reason is as follows. I can make two types of mistakes. I can add a variable that really is a noise variable. And well, I know I can evaluate that, the probability of that, if I believe in this calculation is 10% here, that it's selected even though it's just random noise. That's one type of error I can make. And the other type of error I can make is I don't include the variable even though I should have. Now, this second type of error is more serious because it will lead to biased estimates. You're leaving out a variable, which effectively means coefficient is 0, whereas really it should be some other value that's not 0. And because by leaving it out, your estimates become biased. Because I'm worried about that more than adding a noise variable, I want to be parsimonious, meaning I don't want too many variables. I want few variables, but I want to do that cautiously. I don't want to be too aggressive. And in order to be not too aggressive, I decided to back off of my 5%. And I'm saying, if you are significant in 10%, I will include you just in case, by random chance, you didn't quite get the significance level you deserved, but you're still important. All right. Now, after having said all of this, if you choose 5% instead, that's a perfectly reasonable choice also. Okay, that ends this segment.